Okay, you're probably watching this in the year 2040 or something like that. But this is 2020 right now when I film this, and right now we're in the middle of the COVID infection, COVID pandemic. And I wanted to show something about how this parallels the concept that we're going to talk about, which is acceleration. Because every day, the amount of data that we're seeing in the paper and the news and so forth is just overwhelming, and they change the concept all the time. If you just look at the cases increase for a while in the spring, and then they're increasing more. They're testing more, but they're increasing more. And so the total number of cases is changing as time goes on. It's going to continue to increase, right? Because the total number of cases, they're not talking about how many people are sick right now. They're talking about how many have we measured total. And it just keeps adding up. Well, they decided that a good way of looking at it is not to look at this. That doesn't tell you as much. And they talk about cases per day, new cases every day. So this is one of the ones you see an awful lot now, is if you're getting a whole lot of new cases per day, that means things are getting a little worse case-wise. And so really this ends up being the slope of this graph. I mean, they release new case information from hospitals all the time, so it's a lot easier to get this, but it ends up being the same thing as the slope of this, the change in cases, in total cases per day. Let me write that as total. So this is kind of like this. You've got, if you had something moving along, and let me just have it doing that. If you had something moving along here, and starts at some position 0, and it's not moving very much at first, then it's moving farther and farther and farther. It's moving at a pretty quick rate. Our velocity might look like this. Let me try to get it like this, and then it's slowing down a little bit, so maybe it comes back down like that. Okay, so this velocity is the change in position per time. It's the slope of this, just as this is the slope of the total cases. Well, then they said, well, wait a minute, we're going to be getting new cases all the time. People are going to get infected. You can't stop all infection. So then they said, well, wait a minute, how about this? How about we look at the change in cases, delta, change in new cases per day, every day. Okay. So at the beginning, things were getting worse. You had a whole lot of new cases per day. The rate of new cases per day was pretty high. Then it calmed down a little bit. You can see the new cases per day decreased. So you were actually getting fewer new cases every day. Then we started having more new cases every day. And now we're at this point where it's actually going down a tiny bit. And this ends up being the slope. You could look at that as the unit as being cases per day. Day times day is day squared. It's a weird way of looking at it, but I just want to show you experience this I shouldn't say currently. If it's 2040 now, you're not experiencing it currently. But in 2020, we were experiencing this all the time. They never said that. But the change in new cases per day was an acceleration. It was a change in the speed at which we were getting new cases. So let's look at that. We had the velocity was the slope of the position versus time graph. So it's the change in position or displacement divided by time. Acceleration is just, and we write A, and the unit is going to be meters per second squared, as you're going to see, is the change in velocity per unit time, or the slope of the velocity versus time graph. Okay, and if we look at that, this has unit meters per second. Sometimes we write units in brackets like this. This has units seconds, so it's meters per second per second. How much does the velocity change every second? But we write that as having a unit of meters. We group the seconds. Meters per second divided by seconds is meters per second squared. So acceleration is a measurement of the rate of change of the velocity. How much of the velocity is changing every second? We find that from the slope, right? So that would have a slope, something like this. I wish I'd used a different color. It's not too late. Okay? For a little while, I should make sure that this corresponds to that. And then it has a negative slope, so it would kind of go like that. Okay? So we get the acceleration from the slope of the velocity versus time graph, or if we have data, we can use delta V over T. Now, let me do that. Let me talk about how we use this in equation. I'm definitely going to double back. We're going to go over these graphs over and over. But I want to show it's the rate of change of this base of, excuse me, it's the second derivative if we want to talk about calculus. It's the rate of change of this thing, which is itself a rate of change. It's a weird thing. Some people think going fast and speeding up mean the same thing. They really don't. Going fast, you can go 20 meters per second. That's pretty fast. That's about 40 miles an hour, right? Or you can have a big acceleration without very much velocity, okay? You could have an acceleration where you're starting from rest and speeding up. So this is the change in the speed or velocity. This is the change in position as a function of time. Let me show you how we use this in an equation. Remember, the delta means change in. So our equation, and we're just going to do, wow, that's tough to erase. Our equation is A equals delta V over T. But delta V is change in velocity, and change in anything is going to be the last one minus the first one. The way we rate this in AP is A equals V minus V0. Remember, this means where we are at the end. We assume the whole problem's happened. What was the velocity at the end? Minus the initial velocity, V0, divided by T. So if I know I am going 2 meters per second, and I speed up to, and let's just assume it's all in the positive direction, 6 meters per second in 10 seconds, my acceleration would be, this would be V0, this would be V, label those variables, this would be T, would be, substitute in, 6 minus 2 divided by 10, that's going to be 4, that's going to be 0.4 meters per second squared. And we can do this in any order. If I have any 3 of those 4 variables, I'm going to be able to find the 4th. So let me do one more. I know you can pause if you need me to stop. Okay, I have an acceleration of negative 10 meters per second squared. 10 meters per second squared in the negative direction. Remember, this is how we're doing direction now. Okay, my initial velocity is 20 meters per second, and my time is 3 seconds. As we're going to see in free fall, this is a case where if I throw a ball up at 20 meters per second, that's the acceleration due to gravity. And if we do that for time, we want to find what V is. And I want you to get in the habit of writing this. It's good to know what variable we're looking for. Okay, so if I write this down, A equals V minus V0 over T. Negative 10 is A. V is my question mark. I'm just going to leave it as V. Minus 20 over 3. I'm going to leave out the variables because if these are all in happy physics variables, meters, meters per second squared, seconds, things like that, then my result will come out in happy physics variables. So 3 times negative 10 is negative 30 equals V minus 20. I add 20 to both sides and I find that V equals negative 10. Unit has to be meters per second if I was consistent. So that's how we use acceleration. In the next lesson, I'll talk about free fall, and I'll show you some tricks for finding some, doing acceleration a little easier.